So, hi guys, my name is Mustafa. I am currently an ECE 4th semester student. So, today we are going to be looking at programs and arithmetic operations. So, the aim of the experiment is to write an assembly level program to perform 32-bit addition, subtraction, multiplication, and division on operands stored in RAM locations. So, there's a few things that you guys need to know before we go to the explanation of the program. So, first of all, there are 13 registers on the STM32F4 board that you can access and perform operations on. They are from R0, R1, R2 till R12. And these registers are outside the RAM memory locations. So the starting location of the RAM addresses where your data is stored is 0x2 followed by 7 zeros. And all the assembly level instructions that we come across in this program, explain we'll be looking at the explanation of them as and when we come across them throughout the program. So coming to the algorithm, so first we will load a register with the RAM location address 0x200, where we will store the condition to as to what operation we're going to perform. 1 for addition, 2 for subtraction, 3 for multiplication, and 4 for division. Then we will load the two 32-bit operands in the subsequent RAM locations, and we will check the condition which we need to perform, and then we will store the result in subsequent RAM locations, and we will loop forward to terminate the program. So the coming to the program, the setup part, uh, I think you would have come across this in your previous experiments or in your theory classes. So we're gonna briefly go through them. So first line says preserve 8. So this maintains 8 byte boundary between data. Then you have stack EQ this value. So this assigns this value to a variable stack, and this means 256 bytes. Then you have your areas. So this is the area name stack. This is telling you what kind of data is there in it. I mean, what kind of things are there in it, like either data or code, or no in it means it will be empty. And then read write or read only will be your permission. So in your stack, you have stack mem space stack. So this will create a space which will be filled with all zeros of size stack, which is 256 bytes. So stack mem is your space that will be 256 bytes in size. Then you have your area reset. Here you have export vectors, and you have DCD stack mem and DCD reset handler. Then this is where your code starts in the area dot text. So you have entry, and then you export reset handler, and you have reset handler end. Then this is where your program starts. So you have we store this memory location into register R1. LDR means load data from memory to a register. So this value will be stored in R1, and then we're putting that the value in that memory location to the register R2, and R3 will be R1 plus 4, the value in that location, and R4 will be R1 plus 8. Then what we'll do is compare R2 to 1. So if uh, R2 is holding what operation you're going to perform. So if the value of R2 is 1, this is what comparison we're doing. Now BNE check sub, if the previous comparison results in a not equal, then we will branch to the check sub label, which is over here. And if the comparison results in true, we will go to the next line. So the next line says ADDS, which means add and also update the carry. So ADDS R7 is equal to R3 plus R4. And then we will branch to last, which comes towards the end. Then we have the check sub label. So in this we'll compare R2 to 2, and if the result is not equal, so branch not equal, we will branch to the check multiplication label. If the result, if the comparison results in true, uh, we will perform SUBS, which is subtraction with borrow. So if there's any borrow, that will also be included. And we have R3 is equal to, sorry, R7 is equal to R3 minus R4. And then we have branch to last. Then we have the check multiplication label. Here we will compare R2 with 3. If the result is, if it results in a not equal, then we will branch to check division, or else we will perform UMULL, which is unsigned multiplication long. So because the multiplication can result in a number greater than 32 bits, we need two registers to store the result. So R7 will carry the lower 32 bits and R8 will carry the higher 32 bits. So R3 into R4, and the result will be put into R7 and R8 accordingly. And then we will branch to last. Then we have the check division label. In this, we will compare R2 with R4. If it results in a not equal, we will go to last. And if not, then we will perform unsigned division. R7 is equal to R3 by R4. And then we have last. Here, we will be storing the result, which is R7, to a memory location R1 plus 20. And if the multiplication is resulting in more than 32 bits, R8 will also be there. So that we will store in R1 plus 24. Then we have the label stop, and in that we branch to stop. So this will be an infinite loop which will keep your code running. And then we have end of the code. So now we'll look at how to perform all this in Keil Microvision. So I'll open up a new project. I'll open up the project which I've created. I'm assuming you all know how to set the options for target and all that. I'll add the file. So you can press F7 to build your saved it. And once you have 0 errors and 0 warnings, you can go to the debugging part of it. And you have to make sure that you have all the alignments right, or else you are going to be getting errors. So coming to the debug, you can press Control F5 to start debug session. So here you can see all the register values as you execute each and every line. And if you don't have this memory window, you can go to view and click on any of the memory windows. Then you can put the memory location here, and then to perform addition you can enter 1 over here, and next to places will be your operands. So say I give something like this, and yeah, so to run you can press F5, or you can perform step by pressing F11, and you will be executing line by line, and you can look at the changes in the values of the registers at every line. So first the value of R1 gets updated, then R2 becomes 1, which is the operation that we're going to perform. Then your R3 and R4 get updated with the two operands. Then when your comparison happens, we go to the ADDS part, and then your result gets stored in R7. You can see that the addition of the two operands, the result is stored here. And then we branch to last and update the output into these two memory locations, which is R1 plus 20 and R1 plus 24. Similarly, you can perform multiplication, division, and subtraction, and you can verify your outputs. Next Vedram is going to be explaining you operations on 64-bit operands. Thank you.
Hello everybody, my name is Vedram. I'm currently studying in 4th semester of the Electronics and Communications department, and I am going to be explaining the assembly program from the lab, which is basically arithmetic operations of 64-bit numbers. So the problem statement given in the lab manual here is to write an assembly level program to perform 64-bit addition, subtraction and multiplication on operands stored in RAM locations. Now before we get started, it's actually ideal to always have a good memory map of what's actually happening. So I'll use this thing here. So we know that the stack memory starts at this memory location, right? 0x2 000 and we know that the STM32 is a 32-bit microcontroller, but here they're very specifically asking us to do 64-bit arithmetic. Now, because the STM32 is a 32-bit microcontroller, implies that the registers on the STM32 is only 32 bits long. So if we have to do any sort of 64-bit operations, which means we have to use two registers at a time to represent one number. So which is exactly what we'll do. So first let's get started with the RAM locations where we want to store our numbers. So the three operations given is addition, subtraction and multiplication. So as I said that we need, so each 4 memory locations is 32 bits, right? It's 4 bytes. So we use 8 total bytes of the stack memory from 4 to 8 to represent the first number, and from C to 10, all this is hexadecimal because it's represented by 0x, right? So this is 10 is actually 16 in decimal. So from C to 10 is the second number. So what do we actually store in 0x2 000 is the operation that we want to perform. So if it's 1, it's addition. If it's 2, it's multiplication. If it's 3, sorry, if it's 2, it's subtraction. If it's 3, it's multiplication. Right. So what the code that we're writing is, assembly level code is writing is, it will first see what the operation code is and then do the necessary operation on these two, and then whatever value it gets, it's stored in the subsequent memory locations, right? It will be stored in 20, 24 and so on, right? So let's get to the code itself. Oops, my bad. So if you get to the code itself, you know that any assembly code is of two parts. One of the assembly directives and one is actually the code itself. And like by this time, you should be familiar with the pre-assembly directives. Preserve 8 actually sets the, aligns the stack to be 8 bits long. And then we make a stack space equivalent of 100 hexadecimal bits. And then we create an area for stack with the two settings of no initialization, that is for read write. One area for reset, which contains data and read only, and then the vectors, that will be the global variables throughout the program, and then dot text, which is actually the code, which will also be read only, will be stored in the ROM. The reset handler, what actually comes when you press the reset button on the debugger or the microcontroller. If you do write this to the microcontroller, when you press the reset button or power it on, this is where the program actually starts. Now getting to the program itself, now I told that how this memory location actually determines which operation we're using, right? So we'll first consider this only. The first register R1 is assigned to this memory location, and R2 is pointing to the data that is in R1. So R1 will contain the address, this address, and the square brackets basically indicates the data, like R2 will be loaded with the data that's inside this address. So that will be 1, 2 or 3, right? And then R3 will be loaded with R1 plus hash 4. So basically 0x2000 la 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 all the way up till 4. So R1, R2 will store this address, right? The lower LSB parts of the first number, and R4 will basically contain this address, so the MSB parts of the first number, and then similarly the second number LSB bits is stored in R5 and MSB bits are stored in R6. So basically R1, R2, R3, R3, R4, R5, R6 basically contains the numbers. R3 and R4 contains the first number, and R5 and R6 contain the second number. R2 actually contains which operation that we're trying to do, right? So first we actually compare what is in R2 If it is 1, we go for the addition block. So we know, right, if we have BNE and then something here, this actually refers to the block of code. So if it's check sub, it will go to subtraction. If there's a BNE, it will go to multiplication. Again, if there's a BNE, it will go to default. So we'll get to that one by one. So first it checks if the value of R2 is 1. So it's basically checking if it conforms to addition. So if there is a 1, it will continue with this block. So BNE basically checks if the above thing was equal or not. If it was not equal, it will skip the first case and go to the second case. So it will go to the subtraction block that we'll see later. So the first case, if it is equal, it will come to this part of the code. So first what it does is it adds what is in R3 and R5 and stores it in R7. So we know that R3 is this one. Actually helps to write it. And R5 is this one. Right. So basically it takes the lower parts of the number, the LSB parts of the number, and adds them together, but also puts the carry flag for it, right? Because we need to carry it over for the next register also. And then it multiplies it adds the upper bits also, R4 and R6. So it adds the R4 and R6, which is basically the MSB parts of the 64-bit number along with the carry. Adds will basically set the carry flag and ADC will add but take the carry flag into consideration. So if there is a carry, it will be reflected in R8. So now R8 and R7 contains the added numbers, right? So that is stored here, and after this will go to the last block, B last block. So if we actually had 2 in R2, so now we enter the, so now if there was 2, it will come here, it will see that it was not equal to 1, and then it will go to the subtraction block. In the subtraction block, it will compare if R2 was equal to 2. If it was not equal, it will go to the multiplication block and go check there. If it was equal, we'll come here, same procedure as the addition block, subtract R3 and R5 and store it in R7, and if there's a borrow flag, it will set it, that's why the S is there. And then R4 minus R6 is stored in R8, but this time it will take the borrow flag into consideration. It will consider the borrow into consideration. After that, it goes to the last block, right? So addition and subtraction are pretty much the same, they follow the same pattern. Now if we go to multiplication, now it will check if the R2 is equal to 3. Now here, if it was not equal to 1, 2 or 3, then it will go to the default block, right? If B of not equal, then it goes to the default block that we'll get to in some time. This is the next block. So UMUL is basically unsigned multiplication of a long. Now with the case of multiplication, they have actually given a ready-made thing to store in 64 bits. You don't have to do it twice like subs and SBC. So what it does is it multiplies R3 and R5 and then stores it in R8 and R7. Same thing, R3 and R6 it multiplies and stores it in R9 and R10. R6 and R3, R4 and R6 it multiplies and stores it in R6 and R3. And then we follow the same procedure that we followed in the addition and subtraction parts. We will add R8 and R9, store it in R8. We will, but it will set the carry flag, and then, so basically we are just dealing with partial products at this point. So then we will again consider the carry that was there, add R10 and R6, store it in R9, and then R3 and we'll add it to 0 with the carry, and then store it in R10. There's one more unsigned multiplication of a long that's stored in R5 and R3. So we just add and multiply the partial products till here, and once that's done, we go to the last. Now in a case where we didn't furnish this address with 1, 2 or 3, it goes to something called default. So in default, what happens is it basically stores R7, R8, R9, R10, which is basically where we are storing all the temporarily storing all the results. It just moves it with 0. So like there's nothing is happening. And after addition, subtraction, and multiplication, it basically goes to last, and last basically stores the answer of the arithmetic operation from the register and puts it in memory. So R1 was actually 0x20000000, right? Now it basically takes R7 and puts it at 20 bits ahead of 0x20000000, which is basically 0x20000020, and then R8 will be put at the 24th bit, 24th, and then R9 at the 28th bit, and R10 at the 32th. So for addition and subtraction, you will only need these two. But in multiplication, because we are multiplying two 32 bits, two 64-bit numbers, it will like the number can go for 128 bits. So we're taking the last four. Now we will go to the execution in Keil. So in Keil, we open a new microvision project. Just experiment 2B in my lab. And we choose the exact microcontroller that we want to simulate. So the STM32F407 VGTX. Okay, all default settings for now. Open source group 1 and create a new assembly file. Add new item, assembly file. I'll just call it ABC. And I will copy paste the code from here. So I have copy pasted the code over here, and I will build it. So as you can see, you have to got 0 errors and 0 warnings. Once that is done, go to your settings, go to debug and select use simulator, very important. Press OK. Once that's done, go to your debug, start stop debug session. So now we are in the debug session, and you can actually see like exactly how the LDRs and all work in the disassembly window over here. So in the memory window, we will go to the memory that we've been talking about so long, 0x20. Right. So one thing we have to do is, because we're dealing with only unsigned integers, we have to set the whole process to be done by unsigned integers. So right click on those addresses and go to unsigned and just press integer. So it will become like this. So this address will contain the operand, 1 for addition, 2 for subtraction, 3 for multiplication. This will contain the LSB bits of the first number, MSB bits of the first number, LSB bits of the second number, MSB bits of the second number, right? So let's say I want to add, okay, I'm not going to say this, but let's say, you have to read this backwards. It will be 0 0 0 0 0 0 1 0 0 0 0 0 0 0 0 1, and I'll just put the same numbers here. Right. So we have to add these numbers and these numbers, and they will be stored in this and this. So if you go onto the top left here, we'll run it and then stop the execution. Right. So you can see that the answers have come here, the addition answers. You've gotten the 0 0 0 2 0 0 0 0 2. Right. So addition is happening properly. So you have to exit the debugger, enter the debugger again, go to the memory address that I told you, set it to 2, okay, do the same process. Now 2 is for subtraction, right? And I will run and stop. Now I've put the same number in both N1 and N2, so the answer is 0 only, so we've gotten 0. So do the same thing again for multiplication. We will start, we'll stop the session, start the session again, go to that memory address, set it to 3, okay. Start and stop. Now you can see that the product has come in the next 4 registers. It's totally 128 bits. If you max out all these bits, all these bits will also get maxed out. So that's the also the registers have the intermediary partial product values also here, so you can check this out on the left side. So that's it for this experiment. Thank you so much.